This lesson is about the first steps we must take to do ARIMA modeling. That is why it's called ARIMA Part 1. There will be ARIMA Part 2 and Part 3 in future lessons. So the first steps of ARIMA modeling are pre-transforming to stabilize the variance of the time series and then differentiating to account for trend and for seasonality. So in this lesson, we're going to introduce those first steps: pre-transformation to make the variance almost constant, and regular differencing to account for the long-term trend, seasonal differencing to account for persistent irregular seasonal effects. And then, although it's not the focus of this lesson, we will look at the ACF and the PACF and alert you that we will eventually need the PACF as well, which we'll learn in a future lesson. ARIMA modeling operates very different from decomposition. ARIMA relies on differencing of a variance stationary series to obtain random term. And that's what we do in this lesson, achieving a stationarity in the variance and differencing. That's what is being illustrated here, excuse me. In this lesson, then, we are going to learn how to do differencing. And why is it important that we know all that? Well, ARIMA is a very comprehensive approach to modeling time series. It's one of the most popular methods of time series ever. And it's been there for many, many years. And being a practitioner in time series requires that you are good at it. The ARIMA model has the advantage that it accounts for trend, seasonal, and random component of a time series that has approximately constant variance, but with an approach that is very different from the decomposition approach that we learned earlier in other lessons. So ARIMA, apart from being very important in terms of practice, relies on differencing a constant variance time series to obtain a random term like we did in decomposition. And then it's going to use the sample ACF to diagnose whether the random term is stationary. After that, it will use the ACF and PACF to identify a model and then incorporates what's learned about trend and seasonal to model the time series, accounting for them as well. So it's a long process. Today in this lesson, we only focus on the very, very beginning of this long process. So it's doing the first steps right, like we are describing them in this lesson, is crucial, okay? Very important to start well when you are doing modeling. ARIMA indeed is the benchmark against which all models approaches to forecasting are measured. So we want to understand it well to use it to forecast. So what are the first steps? What is the first step in ARIMA modeling? The first step is always going to consist of looking at your time series. Of course, you always look at your time plot. You inspect and diagnose your time plot, and then you examine its features. Well, it has a trend. We are looking again at the Johnson-Johnson time series that comes with R. We see that it has an upward trend. There is increasing earnings, and then there is a seasonal whose amplitude increases proportionally to the trend over time. So it looks at first glance, by looking at the plot, that the variance of the time series is increasing. So the time plot, we conclude, has trend and increasing variability. So if you're going to do ARIMA modeling, that means that we have to do, before we do differencing, we need to pre-transform the time series to make that variance a little more constant. Doesn't have to be exactly constant, that's very hard to obtain, but we must take care of this variance first. So I took the log of this time series. So differencing, pre-differencing transformations to make the variance almost constant that are typical are the log transform, the square root transform, box cost transforms. There are very different transformations, and you want to keep it simple when you are working with a time series. So I just took the log to get started, and I tried that, and it looks like the variance has stabilized. What we see now is that we see as much variability at the beginning as at the end, although we have this middle part here that is kind of ruining that. We could try other things such as a square root, but I'm going to leave it at the log so that I just illustrate the process. Of course, later on we can try other things to see if we can do better. So the log transform seems to do the job. So we will continue to work with the log time series. So you have to be keeping track of what you're doing to the time series, because when you're modeling, eventually you're going to have to remember to do good forecasts. Okay, so we are okay with it, let's say, and just realize that not all time series need to have a pre-difference in transformation. We did it here because there is obvious increasing variability in the time plot, and a log helped us sort of make that variability a little more homogeneous than it was in the original time plot. So you need to do this. You plot your time series, and then next to it, you plot your transforms. If you do more than one transform and you are choosing among several transforms, then you have to tell us, okay, and illustrate it with a plot. So if the variance doesn't seem to be increasing and decreasing, however, you don't need to do a transform. Don't just overdo it. Don't try a transform if your data does not need it, okay? The second step in ARIMA model will be what is called regular difference, the time series. So if the time series has been pre-transformed, to stabilize the variance, you need to regular difference the transform time series. If it hasn't been pre-transformed, you just do it with the original time series. Okay, and that will be to account for the trend. The Johnson-Johnson time series has a trend. So we say that the first order difference of time series values x1, x2, x3, xn, that's how we denote our time series, are a new time series that will denoted by y1, y2, y7 minus 1, such that the new series is obtained by taking the difference. In other words, calculating the change. Yeah? So the first difference, the first order regular difference, is just really a new time series that instead of the time series contains the change from one value of the time series to another. So for example, y sub 1 will be x2 minus x1, y sub 2 will be x3 minus x2, and so on. So change sometimes is more interesting to people than the actual values of the time series. So that's interesting too. So the first difference, actually, if we take the first difference, that's often enough to convert a time series with a trend into a stationary time series. And we say it stationary in the mean. I mean, in other words, remove the trend without trend. If that's the case, then we say that the time series, that the regular differencing has made the time series mean stationary. Okay, so we have names for everything in time series. Well, the regular differencing achieves that for us. Okay, is making whatever time series you're applying it to mean stationary. If you're successful, you have to inspect that. Okay, so the operation of regular differencing, that is calculating the change in a variable, we have this lower triangle, right? This inverted triangle, a symbol that's called the difference operator. Okay, remember we had a backshift operator, and we also now have a difference operator. And we write it like this: a difference operator applied to xt converts the xt into the change in xt, and we call the change something else. You don't want to keep the same names for variables that have been transformed, because then it's very hard to keep track of what has been done. You have to be a good record keeper, because all these steps that we do need to be reversed afterwards, okay? So let's illustrate that with the logged first observations of the Johnson-Johnson time series. So let X denote the logged earnings, because remember we took the log to stabilize the variance of the Johnson-Johnson time series. And here is the log time series, okay? So I put the R code that I use here, X equal round. I rounded because R gives a lot of decimals, so there is no space here to put them so precisely, to put the numbers very accurately. So this is just for illustration, round of the log of Johnson-Johnson. So we have the Johnson-Johnson, and what we are going to do is take the first order difference of the log Johnson-Johnson. Okay, so if we denoted the log Johnson-Johnson X x1, x2, x3, the new series, the change, this change in the log, the change in the log is going to be the first difference, the first regular difference. And we obtain the first regular difference, the change, by using the function diff in R. So diff, your time series, and you're going to do first difference, so that the argument is log equal 1. And if you type y after that, you can visualize, you can view the whole time series. Here, I'm just showing the first lines. So they are function diff of time series at log equal 1 will do the first regular difference, calculates the change. So let's look at a few examples. So notice x2 is minus 0.462 in the data set. If you subtract from it minus 0.342, which is x1, okay, remember the x's are here on the left-hand side, you're going to obtain the value minus, minus 0.120, the brown value in the difference time series. If you do x3, which is the third observation in x in the log earnings, minus the second observation in the logged earnings, you're going to have the green observation in the difference time series. If you sorry about that, if you take the fourth observation in the logged earnings and subtract from it the third observation, so in other words, you calculate the change from Q3 to Q4, that gives you the value, the blue value in Q4. So notice how, as we difference, we are losing observations again. So this is like when we did the composition, when we did the moving average, we also lost information, remember? So difference, you lose information for different reasons, right? So after differencing, after regular differencing, you check the time plot. Now the time plot looks like it has no trend, right? No upward trend. The upward trend has disappeared. We basically have the trend in the time series, but at the same time, we have gained the information that the first difference makes the time series at least mean stationary. And that needs to be incorporated when we do modeling. So R needs to know when we do ARIMA modeling that we have a first order difference, kind of trend in this data. But we noticed something else. We noticed that the seasonal hasn't been captured, right? So, and also we just sort of see here, this kind of variabilities is not very constant. So let's ignore that for now. And let's see if the seasonal takes care of, because our time plot showed that there was more regular variability. So let's see what's going on. So the thing is, we see the seasonal and some indication, okay? So let's just focus on the seasonal. The third step in ARIMA modeling, then, if there is seasonal in the time series, will be to do seasonal difference to account for the seasonal, okay? And so we logged the time series and did the first regular difference because there was a trend in mean, and there is a seasonal signal, then we will need to do what is called seasonal differencing. The seasonal differences are very similar to the regular differences, but the lag by which we difference are different, right? So they have to be according to the season, right? So so we will similarly obtain, let's continue what we were doing. We had logged and we had first regular difference of the earnings in the Johnson time series, and we obtain a time series Y1, Y2, Yn. Now we have to obtain now a new series that is going to be the result of seasonal differencing, and we are going to call, following my advice, please change the names if you transform, of the names will be Z1, Z2, Zn minus 1. So Z1 in the Johnson will be Y5 minus Y1. C2 will be Y6 minus Y2. In other words, if you notice, what we are doing is it's quarterly data, because it's quarterly data, is kind of subtracting 1/4 from the quarter the previous year, 1/4 value from the quarter value the previous year. And that will take care of accounting for the seasonal. It depends on the frequency of the time series. If it had been monthly, we would have taken Y12, right? Y13 minus Y1 and so on. We will have maintained a lag of 12. So the operation, the seasonal differencing operation, CT, is going to be the time series YT minus K, where K will be the seasonal, if it's a monthly time series, or the frequency of the time series. If the time series is 12 monthly, you use 12. If it's quarterly, we use 4. That's why we used here Y5 minus Y5 minus 4. And here Y6 minus 4, and so on. So that's very important. Although it's also regular differencing, and the operator is called also differencing operator, is the seasonal operator, then we denote it by the K, because the K is the lag by which we difference. Very important that you become familiar with this notation. Okay, so let's do the seasonal difference of the first difference, regular difference of the log earnings. Okay, so here is the first difference of the log earnings that we calculated in a slide before. So it's the diff of X lag equal 1, right? So this was the log difference, the first difference of log earnings. And now we calculate the seasonal difference. Now, notice how the seasonal difference we start in 1961, not in 1960. We lose much more information, we look at more observations when we are doing seasonal differencing. Okay, so this will be diff of Y, and the lag is equal to 4. So that's the that's the seasonal differencing, and that's the R code for doing that. Now let's look at a few numbers. The Z1 is the blue number in the seasonal difference, the time series. Will be it will be the Y5, right, 0.123 minus the Y1, which was minus 0.120, and that gives us 0.243 in the seasonal difference time series. So you can match the colors of the calculations to the number that we obtain in the seasonal difference time series. Okay, the one on the right is the seasonal difference time series. The purple then is Y7 minus Y3. So we start then the new series in 1961. And now when we look at this, you see around 0, you have some series fluctuating sort of randomly around 0. That looks more like what we're looking for. So we are looking for a time series that has a mean that is approximately constant. In this case, it looks like the mean is 0. The time series fluctuates around 0. The variance, we did our best with the log, and the variance should also be approximately constant, or not increasing or decreasing, or periods that have a lot of variability and others that have very small. This one looks almost, you can say, constant and not perfect. We should have tried other pre-transformations, but let's say that this is acceptable. It's acceptable, and we have stabilized the variance. So now, before we do the next step, we should be convinced that we are happy with the variance and the mean being approximately constant. And what we are doing now in the next step in the ARIMA modeling process is to start looking at the ACF. Does the ACF support the conclusion we reached that the variance, that the mean of the time series is constant? So that will translate into a sample autocorrelation function of a stationary model. Okay, so we look in the next step, the fourth step already, observe the ACF and the PACF of the random term left, and then identify a stochastic process. That will be if you will not need to do that right now, but this is just saying that the trend is first order, and there's a typo there. The seasonal is of first order, and the model for the random term is regular MA1. And I'm telling you that because I have a lot of experience identifying ARIMA models. I can tell them, and then I write it like this. So I'm gonna fit an ARIMA model of these features with these features. So I base that on two things. I look at the ACF, and this is an ACF of a stationary time series, meaning constant mean and constant variance time series. Of course, there are many, many, many different ACFs of different, very, very different stationary processes. So that's something that we'll get used to when we study the theory of a stationary stochastic process. But for this particular one, there's no two time series that are the same. This looks like the ACF of a stationary process. If I'm happy with this conclusion based on the ACF as well as the time plot, then I can go on and look at the PACF and say, okay, now combined with the ACF, I can identify a model for the time series. And that will be the model that I will fit, at least the first model that I will start fitting and use it for forecasting. Okay, so note about the step 2 that we did, the regular differencing that we did to account for the trend. It could be, remember that we use the operation, the first regular difference, right? Just calculate the change. And sometimes the change will not make the time series stationary. It doesn't capture the trend. In other words, doesn't make it disappear. So we then might be inclined to do further differencing. And that is a little problem, but it can be done. Okay, so for example, we could do the second order regular difference. So that would be the first order difference of the first order difference. And notice how we put this as a square here. So it's the difference operator square. The difference operator square means that we apply the difference operator more than once. So, but on top of other differences. So for example, if we apply the difference operator to the difference of xt, which was the y sub t, right? Then what we're doing, bring the operator inside into what y sub t is, which was xt minus 1. Then we have difference of xt minus difference of xt minus 1. Difference of xt, the difference of xt is xt minus xt minus 1. And then the difference of xt minus 1 is xt minus 1 minus xt minus 2. And that's what gives us, when you solve and put together, you get xt minus 2, xt minus 1 plus xt minus 2. So notice that these higher order regular differences are each time doing first order difference of the previous difference. And we do that in R by always saying that you're doing log 1, so it's a first order difference, but how many times you're doing differences equal to in this case. Make sure you become familiar with the R code. And so we try to avoid in practice to do second order regular differencing because the interpretation is so hard. And we want things that at least we can interpret. So imagine we log the time series. That already loses something because people don't think about earnings as logged earnings. Then we did change. We calculated the change, which is okay. We can still understand change. Then we did the seasonal differencing, so which is okay. It's just saying, well, we're just removing the seasonal term. But by the time we're done with all that, we have our time series that is kind of hard to interpret what the numbers mean, right? So no problem. Okay, don't panic. That doesn't mean anything. When we do modeling, we are going to fit the actual time series, and we are going to, but these steps are going to, this information that we're gaining now has to be incorporated into the model. So as an exercise for you, I want you to complete this table, and the solution will be provided during the meeting that I have with you during the lecture time on Tuesdays and Thursdays. It will be done on Tuesday, and we'll solve it there together. I'd like to use that time, which is not compulsory for you, but the video is, so that we practice further. But I would like you to try it on your own first, okay? And then further regular differencing to account for trend. Let's continue practicing. And could you say what's the expression for the third order difference, which is applying 3 times the first order difference, one on top of the other? Could you do that after the example we did for 2? And also, we will also solve it during the meetings, okay? On Tuesdays and Thursdays, or you can always ask during the office hours. So the good practice in the first steps of ARIMA modeling is to first realize that you do not need to do all the first steps. I mean, learners, first-time learners, they think that they have to do everything they learn. No, your expertise means that you have to make a choice. Is it necessary to pre-transform to stabilize the variance? Is it necessary to difference, regular difference? Is it necessary to seasonal difference? If you don't have a seasonality, why would you seasonality difference? If you don't have a trend, the mean doesn't seem to be increasing, why would you do first order difference, right? So no 2 time series are identical. So you need to customize your practice. That's something that is pretty common when you're doing modeling, right? So sometimes the seasonal differencing takes care of the trend itself. So don't be too rigid if you try regular differencing to account for the trend. And then on the one hand, then you can try seasonal differencing separately without not seasonal differencing on the regular differencing, but separately. And then and maybe sometimes the seasonal differencing by itself without having done regular differencing takes care of the trend. If none of those takes care of everything, then you do seasonal differencing or regular differencing, which is what we did in this lesson. So another advice is keep the orders small, okay? People tend to go crazy differencing. And when people use automated methods of modeling, they also do a lot of differencing. So you don't really know what you're fitting. So for regular differencing, use usually the argument lag equal 1 in the command diff in R, and avoid using the argument differences, okay? So don't repeat it. Don't do it too many times. So don't do second order regular differencing or third order regular differencing. There is this a common sin made by beginner, which is to over difference the time series. So you eventually leave absolutely nothing there to worry about. For seasonal differencing, the same. Avoid using the differences argument. If you do seasonal differencing, you don't want to do it twice. Besides, you lose a lot of data if you over difference. So try to avoid it. So what we learned in this lesson is that we defined the differencing operator and made a distinction between regular differencing and seasonal differencing. And the regular differencing was to account for the trend. The seasonal was to account for the seasonal. So advice was given as to wise use of this, which was that you should not overdo it. Don't over difference. Keep it at small lags and do not use the operator repeatedly. So we learned the steps to take before modeling a time series with an ARIMA model for forecasting for a specific example. We didn't do modeling, we didn't do forecasting yet. That's coming in future lessons. Each time series requires different steps before modeling. So we may have to do it all or none or combinations of the operations we did. So if there's no increase in variance, why would you take the log, right? So you need to make a judgment as to which of these are necessary. Each time series is different, don't forget, and requires a special treatment. We also noticed when we were done that we need more learning in order to identify and fit a model. I told you that the ACF helps me see whether the time series is mean stationary, but and then I use the ACF and PACF combined to identify a model, but I didn't teach you how to do that. We will have to go over the theory of stationary stochastic processes first to learn about the composition of the ACF and PACF of different models, okay? So I hope you enjoyed this lesson, and you will see in the next one how to use the PACF. And what is the PACF more than anything?